Hello everyone, welcome to today's webinar on Unlocking Electric Motor Design Excellence, a multiphysics simulation with EMWorks products. My name is Sumit Singh and I want to thank all of you for joining us today. Over the next hour, we have an exciting presentation showcasing how EMWorks engineering simulation software enables organizations to unlock superior electric motor designs through a virtual prototyping and multiphysics analysis. Moving on, let's briefly outline the agenda for today's session. We will kick things off with an introduction to EMWorks, their history, technology portfolio, and application areas. Next, I will provide an overview of the simulation setup process and multiphysics capabilities using EMWorks software. We will also showcase specific applications and examples. After that, we will go through project case studies focused on electric motor design and analysis using EMWorks tools. Finally, we will wrap up with an interactive Q&A session where you can get your specific questions answered. So, without further ado, let's get started. EMWorks is a pioneering provider of electromagnetic and multiphysics simulation software used across industries worldwide. Founded in 1995 by two PhD graduates from the University of Illinois Urbana-Champaign, EMWorks has been at the forefront of simulation technology for over 25 years. Headquartered in Montreal, Canada, with an additional office in Yokohama, Japan, EMWorks has a truly global footprint. Their worldwide sales network covers the Americas, Europe, and the Asia-Pacific region. EMWorks serves a diverse range of industries including aerospace, automotive, industrial equipment, electronics, energy, and more. Their software suites are tailored to various applications spanning electric machines, actuators, sensors, PCBs, antennas, and other electromagnetic products. The tools are offered via commercial, academic, research, and startup licensing programs to maximize accessibility for organizations of all sizes. Under the hood, EMWorks leverages cutting-edge physics modeling engines and finite element methods to deliver accurate and advanced multiphysics simulation capabilities. Our suite includes solvers for electromagnetics, thermal analysis, structural mechanics, motion dynamics, and electrical circuits. Both 3D and 2D modeling is supported. Sophisticated CAD integration with SolidWorks and Autodesk Inventor eliminate painful CAD import-export processes. Engineers can work directly with native CAD geometry. Additional features include application-specific wizards. We have ECAD, MCAD translators, and transmission line modeling toolkits to enhance productivity. This blend of high-fidelity solvers, tight integration to CAD, and specialized add-ons enables EMWorks to provide enterprise-grade simulation technology accessible to organizations of all tiers. EMWorks offers a range of simulation products tailored to the analysis needs of electrical and electromechanical engineers. EMS 3D provides comprehensive 3D electromagnetic field simulation with optional multiphysics capabilities. EMWorks 2D offers a 2D electromagnetic and thermal modeling for applications like rotating machines. MotorWizard rapidly simulates and optimizes electric motor designs with a customizable template approach. And finally, we have HFWorks, which tackles high-frequency applications like antennas, RF boards, and microwave components. All the tools feature direct CAD connectivity, automatic meshing, vast material data libraries, parametric design optimization, and a high performance computing support. Let's explore some applications areas served by these products. EMWorks targets two primary segments, low frequency and high frequency simulations. For low frequencies, EMS 3D, EMWorks 2D, and MotorWizards are ideal for electric machine design, actuators, sensors, transformers, and other electromechanical devices. Key verticals served include aerospace, automotive, industrial machinery, energy, and consumer electronics. On the high frequency side, HFWorks caters to RF, microwave, and wave applications like antennas, waveguides, and high-speed electronics. Defense, telecom, electronics manufacturers, and research institutions rely on HFWorks for next-generation product development. This combination of low and high-frequency tools positions EMWorks as a trusted simulation partner across diverse industries. Beyond the software tools, EMWorks foster an engaged community of users via conferences, webinars, blogs, white papers, and more. These initiatives facilitate peer learning and promote the exchange of engineering best practices. Users also get access to a public forum to interact with EMWorks experts and peer-to-discussion simulation challenges. For those needing additional support, EMWorks offers specialized design and consulting services delivered by our simulation leaders. Overall, EMWorks aims to be a true simulation partner, enabling organizations to maximize value from their engineering software investments. Moving on, let's discuss why multiphysics simulation is becoming critical for next-gen product development. So, with rising complexity, looking at physics in isolation, using single-purpose tools grows highly limiting. This decoupled approach cannot capture real-world interactions between coupled phenomena like electromagnetics, heat transfer, and structural forces. In contrast, multiphysics simulation provides far more realistic predictions by modeling these interdependencies in a unified environment. This unlocks superior product performance, reliability, and efficiency through comprehensive virtual prototyping. Multiphysics analysis also saves enormous costs by identifying design issues early before committing to physical testing. So, all in all, having integrated tools to simulate coupled physics digitally accelerates innovation across engineering domains. Next, let's outline the streamlined workflow for multiphysics simulation using EMWorks softwares. It starts with the user constructing their CAD geometry, including components, assemblies, and moving parts. Engineers then define material properties for the various objects in their model. Next, boundary conditions are applied. This includes excitations like currents and voltages, prescribed motions, and any external loads. Then, automatic and adaptive meshing tools discretize the geometry into finite elements suited for numerical analysis. With the model setup, multiphysics analysis can be executed to characterize electromagnetic, thermal, structural, and dynamic performance under operating loads. The parametric architecture enables design optimization by modifying variables like geometry, materials, or excitations and rapidly resimulating. Comprehensive visualization and reporting features also allows convenient sharing of insights with decision makers. This efficient process facilitates virtual prototyping of electrical and electromechanical systems with a high degree of accuracy. Now that we have explored EMWorks technology and capabilities, you may wonder what truly differentiates us in the engineering simulation market. Why should engineers and designers choose EMWorks? So let's understand these key differentiators in more detail. EMWorks native and bidirectional CAD integration with SolidWorks and Autodesk Inventor helps to eliminate the pains of importing, exporting CAD geometry, which often lead to data loss or compatibility issues. Engineers get full access to the CAD model for representing complex designs with accuracy. The integration also enables parametric synchronization between the CAD and the simulation environments. Any design changes made in CAD or automatically can be easily reflected in the simulation. In contrast, tools lacking advanced CAD integration often limit the modeling of intricate structures and force engineers to rely on third-party CAD software. The fragmented workflow hampers both accuracy and productivity. EMWorks overcomes these hurdles through its tight CAD integration. Another differentiator is that EMWorks delivers a truly integrated single platform multiphysics solution. Our finite element solver and user interface are unified across electromagnetic, thermal, mechanical, and motion simulations. This means engineers can couple different physics like electromagnetics with heat transfer, stress analysis, and dynamics within a single model. This unified simulation environment brings tremendous efficiency, accuracy, and ease of use benefits compared to using separate tools. EMWorks also provides a seamless workflow between 3D and 2D simulations. Engineers can quickly simplify complex 3D machine or electronic models to 2D for faster computation. This avoids the hassle of recreating 2D CAD geometry from scratch as needed in other tools. Analyzing the same design in both 3D and 2D provides an efficient modeling workflow. Furthermore, EMWorks CAD-embedded tools like EMS 3D can handle the most complex geometries with ease. Users get full access to SolidWorks' advanced modeling capabilities. Intricate components, curved surfaces, and small features are represented accurately, which is critical for real-world electromagnetic performance. Detailed CAD modeling coupled with automatic meshing enables high-fidelity virtual prototyping. Tools lacking native CAD integration often struggle with importing and meshing complex geometry from external CAD packages. EMWorks overcomes these limitations through its direct CAD access. EMWorks integration with the CAD modeler also enables powerful parametric modeling workflow for design optimization. Engineers can define geometry dimensions, material properties, mesh parameters, and other attributes as variables. These parameters can then be modified and simulations rapidly rerun to evaluate design changes. Next, EMWorks also provides exceptional technical support and services customized to each client's requirement. Their simulation experts offer timely assistance online or over the phone for any technical challenges users face. For unique analysis needs, EMWorks can develop customized features leveraging their decades of multiphysics expertise. These value adds aim to help customers maximize their ROI from EMWorks software. Moving on to application examples, let's look at an electromagnetic simulation project for a permanent magnet synchronous motor design. Some key challenges include modeling different pole and winding configurations, calculating torque production and back EMF waveform, evaluating temperature distributions under load. So using EMWorks 2D, engineers modeled the motor in CAD with precise geometry. Leveraging coupled magnetic and thermal simulations, they were able to analyze flux linkage, cogging torque, magnetic field strength, back EMF profiles, resistive losses, and temperature rises under operating conditions. This multiphysics simulation provided invaluable insights to optimize motor design for higher efficiency, torque density, and reliability. This project illustrates how EMWorks empower engineers to develop superior electric motors through comprehensive virtual prototyping. Here we see some visual results from the permanent magnet motor analysis in EMWorks 2D, including magnetic flux linkage distribution, back EMF waveforms, magnetic flux density contour plot, and stator temperature profile under load. The ability to evaluate such detailed electromagnetic and thermal characteristics in the virtual world even before physical prototyping provides huge benefits. Engineers gain actionable insights to refine the design, resulting in high-performing, cost-effective, and reliable motors. In the next part of our presentation, we will explore some detailed real-world examples of how EMWorks suite of electromagnetic simulation software products has been leveraged to optimize the design and performance of electric motors and electromechanical devices across diverse applications and industries. These examples will provide a deeper insight into how powerful analysis capabilities of EMWorks softwares like EMS 3D, EMWorks 2D, and MotorWizard to address complex multiphysics problems. Here we have a detailed EMS 3D model shows an axial flux permanent magnet synchronous motor design optimized for use in electric vehicles and wind turbines. The axial flux topology provides high torque density in a compact form factor. Leveraging EMS 3D coupled magnetic, thermal, and mechanical along with motion solvers, the motor was comprehensively analyzed for performance metrics like torque production, efficiency maps, stator temperature distribution, and rotor structural deformations under electromagnetic forces and centrifugal loads. The multiphysics simulation provided in-depth insights to refine the electromagnetic, structural, and cooling design for high power density and high efficiency operation under continuous and on-load conditions for the target EV and wind power generation applications. Next, this EMS 3D application model demonstrates the simulation and analysis of an eddy current braking system containing permanent magnets and a rotating steel core. Key results obtained include braking torque versus speed and power dissipation versus speed curves The magnetic flux density streamline plot also provides insights into the electromagnetic field distributions and eddy current effects in the brake core. Overall, EMS 3D coupled electromagnetic and motion solvers enabled accurate characterizations of the braking torque performance and power losses to aid the optimization of smooth, stable, and controlled braking behavior. Now, let's move to EMWorks 2D examples. This EMWorks 2D model analyzes a permanent magnet-assisted synchronous reluctance motor design like those used in electric vehicles. The 2D electromagnetic field simulation provided in-depth characterization of torque production, losses, vibrations, demagnetization, withstand, and other parameters across the operating speed range. The insights from the virtual simulation helped engineer to refine the electromagnetic design and structural parameters to improve torque density, efficiency, reliability, and control. Moving ahead, this EMWorks 2D application characterizes a linear permanent magnet synchronous machine design which is used in factory automation applications. A comprehensive simulation of the electromagnetic fields and dynamics enabled analysis of key parameters like thrust force production versus position, back EMF waveforms, end effects, magnetic field distributions, and many more. The insights again helped engineer to optimize the electromagnetic design and mechanical parameters for stable, smooth, and precise linear motion control. Moving ahead, MotorWizard is a template-based electric machine design and analysis software that enables rapid modeling and optimization of a wide range of motor topologies. It provides an extensive set of predefined design templates with various winding layouts, slot shapes, rotor configurations, and other parameters that a user can customize as per their requirements. This enables creating initial designs in minutes compared to hours in traditional CAD-based tools. So here we have an example of surface-mounted permanent magnet AC motor design generated using motor design templates. The comprehensive simulation provided insights into torque speed profiles, loss distribution, efficiency maps, and more to determine the optimal design point for the target application requirements. Moving ahead, next we have a MotorWizard application designed and analyzed a switched reluctance machine by simulating torque profiles, flux distribution, inductance characteristics, and more. The insights helped refine the geometry to achieve higher torque density, reduced vibration, and improved control performance. Here are few testimonials from EMWorks customers highlighting the benefits and value derived from leveraging their simulation softwares tools for critical electromagnetics and multiphysics analysis applications. The integrated solutions enabled customers to accelerate product development cycles by optimizing designs virtually before committing to costly physical prototypes. Now, I would like to present a quick brief glimpse of our EMWorks 2D interface. To simulate a permanent magnet motor design inside CAD software, before a simulation can be started, the CAD models of the permanent magnet motor must be built or imported into CAD software. Therefore, we will not go over the CAD modeling steps here instead. Our starting point will be a readily built CAD model which will simply be loaded and analyzed. Our CAD model is the motor assembly with all its parts. These parts include the coils, the stator core, the permanent magnets, and the rotor. Note that we have two additional air parts, one for the air surrounding the motor directly and another outer air component. Once the study is created, the first step is analyzing an assembly in CAD software, is to specify the material types of all bodies. The materials can be chosen from the EMWorks 2D material library or from a user-created material. EMWorks 2D can provide both linear and non-linear materials as well as magnetic materials. The coils are all made up of copper, which is found in the conductor material folder. For any bodies with the same material type, you can apply the material from sketch again, or you can copy the material properties by dragging and dropping it from a previously assigned body. Another way is to select a large set of components and apply the material to all of them. Next comes the magnets. The EMWorks 2D material library contains a folder dedicated for permanent magnets. In this case, a subset of NdFeB N42 is selected for the 6-pole permanent magnets. Magnets have a set of magnetization property, including whether they are permanent, their coercivity, and their remanence. When applying a magnet, it is essential to specify the direction of coercivity. In this example, some magnets highlighted in blue will have a coercivity direction outwards radially. This can be specified by selecting cylindrical coordinates. The others will be directed inwards radially. This can be done by selecting cylindrical coordinates and reversing the direction. Both the rotor in the center of the device and the stator are made of mild steel. This is found in the electrical steel folder. For the two air components, the air material will be selected from the material library. These parts are essential and must be part of the assembly since electromagnetic fields exist in air. When all the bodies have been assigned a material, to calculate the electromagnetic force applied on any part, request the force calculation, which can be done using virtual method, and then select the solid desired. Here we choose virtual work method to calculate the torque on the rotor core. The model meshing is very simple in the EMWorks 2D software. Simply select the mesh size and the tolerance for small spaces. Then choose to mesh the model. Of course, some smaller bodies in a finer mesh than others, so it is a good idea to apply a mesh control to such bodies. The inner air part is a region where fields can be strong, and they reflect the coupling between the motor's part to accommodate the small gaps covered by the inner air. The outer air is used as an enclosure volume. This part should be made sufficiently large to ensure that fields are small enough. One last thing to be done before running the analysis is to set windings. There are two types of windings available: solid windings and stranded windings. In this model, we have selected stranded winding. With current driven type
coils for all the three phases. The amplitude of the current phase A is set as 100 ampere with a frequency of 100 Hz. Similarly for phase B and phase C can be implemented. You can apply the current source as sinusoidal, DC or exponential current, or import the excitation waveform as per your requirement. After all the input is entered, you can run the study, and you can obtain the waveform of the results under the results table tab, and also plots such as flux density, current density, etc.
So, to conclude, we have seen how EMWorks provides a powerful suite of electromagnetic and multiphysics simulation tools for electrical machine design and analysis. The combination of EMS 3D, EMWorks 2D, and MotorWizard delivers sophisticated modeling capabilities across low-frequency applications in key industries like automotive or aerospace, energy, industrial machinery, and more. By enabling accurate virtual prototyping of complex coupled physics phenomena, EMWorks empowers engineers to optimize product performance, quality, efficiency, and reliability before physical testing. The streamlined CAD-based workflows, intelligent meshing, and automatic solvers provide unmatched ease of use benefits to both expert analysts and new users. Additional values arises from EMWorks engaged community, expert support services, and customizations. Overall, EMWorks aims to accelerate innovation cycles by unlocking superior design excellence through engineering simulation. We thank you for joining today's session and hope you find it valuable. Do reach out for any additional questions on how EMWorks can assist your organization in attaining electromagnetic and multiphysics simulation mastery. I thank you for your time and attention today. I'll be now happy to address any questions you may have during the Q&A session.